Thank you for the invitation. I'm going to talk about joint work with Michael Belkin and James Voss, who are here with us in the audience. I am a little bit surprised that I haven't seen many jokes about the fact that on the one hand we're in a workshop on spectral methods and it's happening precisely during Halloween. I expected more.
There is an event going on upstairs with Halloween theme.
The tea or something like that? Yeah. Right.
But maybe everyone's happy.
But I think that's from the center, not from our workshop, isn't it?
Sure, yes.
Right.
Yeah.
No, I mean Spectral Halloween, right? Anyways. So in this talk, in the first half, I'll talk about a new approach to multi-way spectral clustering. And in the second half, I will sort of generalize the ideas of the first half to introduce a new algorithmic primitive that we call hidden basis recovery that encompasses some known approaches and also presents some new approaches to well-known algorithmic problems such as independent component analysis and orthogonal tensor decompositions. So I will start by reminding you quickly about how spectral clustering works and then tell you what's our new algorithm. So what's spectral clustering? You take a graph and then you construct the Laplacian matrix of the graph, which is defined as the, well, I mean, there are several definitions. If you want to see the variations, you can go to our paper, but for now I'm going to only talk about this variation, which is you take the diagonal matrix having the degrees of the nodes, so the matrix is indexed by the nodes of the graph, and then you subtract the adjacency matrix, and then you do something with the bottom eigenvectors of this matrix to get clusters. Let's talk about this more precisely. First, in the case of biclustering of a graph. Say here is a graph with 6 nodes, and here I have the Laplacian matrix. And we think as the biclustering problem, or one could think of it as a certain graph partitioning problem where I want to minimize the number of edges going across from one part to the other. And the advantage of thinking about the Laplacian matrix is that the objective function of this problem can be written as a quadratic form in terms of the Laplacian matrix, what we have here. Of course, an obvious difficulty of this problem is that it has a combinatorial aspect. It's a minimization problem over -1, 1 vectors. So a natural way of thinking about this, and that's the basis, again, of the method, is to relax the integrality, and then the problem becomes a problem of minimizing a quadratic form over the sphere, which, after thinking about this, say, in terms of first order condition, it becomes an eigenvalue problem on the Laplacian matrix. So here is an example where I compute the bottom second eigenvector of the Laplacian matrix, and that gives me numbers, one number to every node of the graph. And one think of the clusters as some sort of result of rounding the entries of this vector, right? The negative entries, we think of them as corresponding to -1, and the positive entries to 1, and this gives us a bipartition. So how does one apply this to data? Well, I have to think, say I start with points in Euclidean space, and then I try to translate this into a weighted graph by thinking of the weights as similarities. This is a possible choice of a similarity, a function of the distance of the points. And then, again, as I said before, I construct the Laplacian matrix, compute the bottom eigenvector, and I use the sign to partition. And for the biclustering problem, this works pretty well. It has decent theoretical guarantees. However, biclustering is pretty limited because it only gives you 2 clusters. So the real question is, well, what if you want more than 2? Then a sort of obvious generalization is to try to use several of the bottom eigenvectors of the Laplacian matrix. If I want k clusters, then I will look at the bottom k eigenvectors. And then I think of these eigenvectors as inducing a embedding of the nodes of the graph in Rk. The embedding is the following. I think of these n-dimensional eigenvectors as column vectors, and then I look as this n by k matrix, and I use the rows as embedding vectors. So this would be n k-dimensional vectors. And I'll tell you in a moment why this makes sense and this embedding is helpful for clustering. But before I tell you that, well, the idea is that somehow some clustering structure will emerge from just the similarities. This was just a graph with not necessarily any Euclidean structure. And then one can, for example, apply some variation of k-means in the embedded space to try to recover these k clusters. I say try because now we see why this is different from biclustering. K-means as an algorithm is initialization dependent, and therefore it's very hard to prove anything about this combined algorithm, embedding plus k-means. However, the motivation as a relaxation of a partition problem can still be stated in this k-way version. So instead of k-means, we're proposing to do something different as a second phase of the method. This is what we propose. So this picture represents how the data could look after we embed it. And the proposed approach is the following. We're going to define a function f on the k-1 dimensional sphere in Rk. And the function will look as follows. It will be some sort of generalized moment of the data. So I think of taking my data points xi. Phi of xi is the embedding. I pick a vector v, a unit vector, and I project the points along this vector v. So this gives me n coordinates. And then I just sum them up, but making them go through a scalar function g. So if g was like the third power or something like that, then this would be indeed some sort of moment of the data, but I'm not telling you, I'm not restricting g to be a moment. In principle, it's any scalar function. So this is what f may look like. So this is like thinking of this as polar coordinates in a way. The claim is that we will find conditions on g so that the structure of local maxima of f recovers the clusters. So informally speaking, the local maxima of f, which are points on the sphere, will be pointing at the clusters. This idea is new when applied to this problem in a way, but we call it contrast function, or I'm using this terminology sort of inspired by similar ideas used in the ICA literature, where there are also directions I want to find in Euclidean space, and one can pick scalar functions like here, so that when I find the maximum of a certain function over the sphere given by these scalar functions, that finds the directions that I care about. So here are the conditions on these scalar functions that make the recovery possible. So I'll make a precise statement of this, about the structure of local maxima in a moment, but I'll explain the conditions first. And for now, I'm going to state the conditions without quite telling you where they come from. Well, this is the so-called hidden convexity that I had in the title, but that I'll clarify later. The first condition and the main one is that the function g composed with square root of x is strictly convex. And then there is a second technical condition on the behavior of the derivative at the origin. Here are examples of functions that satisfy these conditions, minus the absolute value, x to the p for p greater than 2, e to the minus x squared, and the logarithm of the hyperbolic cosine. This function is one of the standard contrasts used in independent component analysis, so that's why I'm mentioning it. It's interesting that we can prove things about it in this context, because in ICA it's some sort of heuristic that works in practice, but nothing can be proven about it. So after one picks such a contrast function, what does the algorithm look like? Well, there are two options. after the spectral embedding, either I do gradient ascent to try to find one local maximum, or if I do it repeatedly, I can enumerate all of them, because as we'll see in a moment, we are not just showing that local maxima correspond to clusters in a one-directional way, but there is a one-to-one correspondence. So this function, the enumeration of local maxima, is not an intractable problem because there won't be that many. Another alternative, again, this depends on the structure of the data, would be to just maximize f over the directions given by the data points. So you see this will lead to different complexity depending on what parameters you are working with. So here is an example of that. At least this makes sense in practice. The first example is on artificial data. The data are these 3 concentric rings from which I construct a similarity graph, and then in turn a function f on the sphere to be maximized, and in the middle I have the resulting clustering from the algorithm, and this is representing the structure of local maxima of f. We see that 2 clusters here correspond to red regions of higher value. And here is another example on real-world data, is an image segmentation example. The objective of this problem is to somehow partition the images into regions having similar pixels. There is no formal definition of what the correct output to this problem is, because generally one compares with segmentation done by humans, and that's what one considers the ground truth. And in particular, well, here we do the segmentation on the graph of pixels of each image, right? Where the similarity is defined as a function of adjacency of pixels weighted by proximity and color similarity. And the contrast function is minus the absolute value. So let me then switch to telling you why this makes sense. This optimization procedure to recover the clusters, there will be 2 arguments. One is properties of spectral spectral embedding itself, this slide, and another will be the hidden convexity I was mentioning before. So first, what happens with spectral embedding that makes this optimization procedure meaningful? So here is a claim that was known before, that if the graph had k-perfect clusters, namely it was partitioned into k-connected components, then the embedding takes a very special form. The endpoints are mapped overall to just k orthogonal vectors, where all points from a given cluster are mapped to a single point. That's the geometric structure of the embedding in this idealized case. And one can think of applying spectral embedding to a more general graph as some sort of approximation to this case, right? So I'll discuss later what we can say about the perturbed case. Now, when one computes the spectral embedding, of course the corresponding eigenvectors computed are not uniquely defined, because these are the bottom k eigenvectors. In the idealized case, these are the eigenvectors associated to the 0 eigenvalue. So they are ambiguous because there is only an eigen subspace. But nevertheless, this geometry of the embedding is preserved independent of which eigenvectors you found. The only assumption is that the basis of eigenvectors that you find is orthonormal. So here I'm being more precise about the geometric structure. In addition to being orthogonal, there is some control over the length of these embedding vectors. The length is inversely proportional to the number of points in every cluster. So we can think of this as some sort of weighted embedded basis, orthogonal basis. And a key identity to understand the behavior of the function f over the sphere is to write it in terms of the original points, which I already did before. just this generalized moment interpretation. But when you use this hidden basis aspect of the spectral embedding, then it also takes the form here on the left and the right. Namely, is a weighted sum of G evaluated at the basis embedding vectors. So here are more precise statements on the structure of local maxima in the idealized case. So let's see. Again, the question is which conditions on G are sufficient and even hopefully necessary to guarantee that the local maxima of F over the sphere are exactly these basis vectors of the embedding up to normalization. So here I'm restating the two conditions I had before. One is some certain strict convexity, and the second is a condition of the derivative of the contrast. So we show the following first, that these conditions are sufficient. Namely, if both P1 and P2 hold, then the normalized basis vectors will be a complete enumeration of the local maxima of F. So this is an if and only if condition. Namely, the two sets coincide. Every local maximum points to a cluster, and there are no additional local maxima up to psi. And more interestingly, the characterization is complete, and we show that these conditions are also necessary. So more specifically, if property P1, the strict convexity property, does not hold for G, then there will be additional local maxima. And if P1 holds but P2 does not, then one of the directions pointing to the clusters will not be a local maximum. I find that one can find such precise characterization quite unexpected. And the particular case of spectral clustering, because technically the claims I made before were for any function having this form. Now, for spectral clustering, as I mentioned before, the weights have a special structure here related to the size of the clusters. And in that case, we can show that P2 is not needed as a property. P1 in itself is enough so that the basis vectors are a complete enumeration of local maxima. So now I'll explain why these claims are true and what is the hidden convexity. So the analysis of the function happens by performing a simple change of variable. Rather than thinking of this function as being maximized over the sphere, I'm going to map it to the standard simplex in Rk. How do you go from a point on the sphere to a point on the standard simplex? You just square the coordinates, right? And if you restrict yourself to the first ortant, then this is actually a bijection. But then the structure of this function emerges when you do that, because now I'm doing maximization over a convex set, the standard simplex. And the condition P1 that g of square root of x is strictly convex implies that now the function f, when I define it as being a function over the simplex, not over the sphere, so after the change of variable, happens to be then a strictly convex function. And up to the business of just restricting yourself to the first ortant, this was a bijective transformation. So the structure of being a local maximum in one setting is the same as being a local maximum after or before the change of variable. And then, if you remember, so this may look a bit strange because I'm doing maximization of a convex function over a convex set. It's not the usual convex programming setting, of course, but this is also somewhat understood. In particular, it is known that for such a problem, the maxima can only, local maxima can only occur at the vertices. So that already gives one side of the characterization of what the local maxima are. The second part, that every vertex is indeed going to be a local maximum, does not follow immediately from this explanation, but is another refinement of this argument. And that would be the proof of the first result. And the proof that there will be additional local maxima if you don't have these conditions is just a matter of constructing the maxima explicitly and exploiting the lack of strict convexity, say, which was property 1.
Sorry, one question.
Yes.
So that inner product can't be negative, like the VC survive?
Well, in principle, yes. I removed and there was an absolute value before in earlier slides, but here I removed the absolute value because I am taking the square root. So, so the function g, first of all, is symmetric, even. The function g is even.
And then what?
Therefore, it's enough to look at what's happening in the first ortant, either for the sphere or for the simplex. So that's why I eliminated the absolute value in this slide. But yeah, there was an absolute value before when I'm actually optimizing, like in this slide. So the algorithm needs the absolute value if you like, but in the analysis I don't need it. Any other questions? So now I'm going to switch to the second part of the talk, which is to see in a broader picture of how this primitive of recovering a hidden basis works and how it actually showed up in other problems that are seemingly unrelated to spectral clustering. So there will be other examples that I announced before, like ICA, independent component analysis. So here is a slightly more abstract way of thinking about what I just said. This is the primitive. There is a hidden orthonormal basis in Rk, so k unit vectors, orthogonal vectors. And this came implicitly from data. I'm going to encode this data as well as the basis in what we call a basis encoding function, which takes the form similar to what I was saying before. There are scalar functions gi. I pick a direction u, a unit vector. I project the basis vectors onto u, and then I evaluate each projection via a scalar function gi. And then I add up all of them. So this is also some sort of generalized moment. And the problem is, given evaluation access to f and possibly a few of its derivatives, find this hidden basis, the vectors zi. So here I'm just restating the example of spectral clustering that we just saw in this language once more. So on one hand, we had a fixed contrast function g that I'm going to evaluate at every projected point, and I add up overall points. That's my function f. And by properties of spectral clustering, this can also be written in this other form where in the ideal case, all points in a single cluster got mapped to a single basis vector, right? So the particular form of gi, the contrast in the basis encoding function, happens to be some kind of weighted version of the original contrast where I weight by the number of points in every cluster. But essentially the picture is the same as before. I'm just renaming a few things. Here is another example, orthogonal tensor decompositions. So for example, say that T is a order 4 tensor, n by n by n by n, which corresponds to a weighted combination of rank 1 tensors, all of them coming from orthogonal vectors. So these Ci vectors are orthogonal. They form a basis. Wi takes into account that the actual lengths may be different. And then the encoding function, the basis encoding function induced by this tensor decomposition problem is just evaluating the tensor at u, 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 u. Which after you write this, it just becomes this function here, summation of wi u.ci to the fourth, which is in the form of the previous one. After you take as contrast the weights times the fourth power. Once you write that, you can try to use what I said before about hidden convexity to think about why power iteration works for the orthogonal tensor decomposition problem. So here is one way of thinking about it. The previous discussion would say that there is a hidden convexity property there because the contrast functions, gi, when evaluated at root t, are quadratic. It's wit squared for the tensor decomposition problem, and this is a strictly convex function. Therefore, as in the hidden convexity discussed for the spectral clustering problem, plus minus the hidden basis vectors, that set is a complete enumeration of local maxima of t of u, 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 u over the sphere. And in fact, the tensor power iteration algorithm can be reinterpreted in this sense as some version of projected gradient ascent with an automatic adaptive step size. So here is another example, independent component analysis that we have seen before in other talks here. So I'll remind you what the problem is. You are given samples from a random vector, n-dimensional random vector x, d-dimensional random vector, where x is a linear image of another random vector s, also d-dimensional, and with the property that the coordinates of s are independent. A is assumed to be a square invertible matrix, and the objective is to recover the matrix A up to certain inherent ambiguities of this problem. Namely, it's not hard to see that you cannot recover the sign of the columns of A, and you cannot recover the permutation of the columns of A. But otherwise, this is a solvable problem. So after a step that is standard in some algorithms for ICA, which is the so-called whitening step, or you could also think it as putting the vector x in isotropic position by using second moment information about x, we can assume that the matrix A is unitary. So the columns form an orthonormal basis rather than the general case. And then the question is to again recover A, but now we know that it's only an orthonormal matrix, so it's the recovery of an orthonormal basis or a rotation matrix. In that case, by the ICA work and standard choices of how to proceed after this first step, one can take as function f, the basis encoding function, the fourth cumulant of x along the direction u. After these transformations, well, in general, the fourth cumulant is just some polynomial over the first four moments, but because I am in the isotropic case, so say I'm assuming that the covariance of x is the identity, then the fourth cumulant takes this form, is the fourth moment minus 3. So it's something I can estimate from my data without knowing the hidden basis, of course. And one can show that by using properties of cumulants, it expands into this form of a basis encoding function. There are scalars, which are the cumulants of the SI, random variables, and then the fourth power of coordinate of u along the hidden basis for every basis element. So it's again some weight times the fourth power in this case. So what do we show about this primitive? Well, first we propose an algorithm. It's not, I mean, in the spectral clustering case, I talked about gradient ascent, and that's fine, and that works. And that's not so original, maybe. Here, instead, we propose an alternative algorithm that we call gradient iteration. It's a fixed point iteration of the gradient of the function f. So this is the iteration. You just start from a point on the sphere and you make it go through the gradient of f, and then you normalize. So this algorithm is an extension of tensor power iteration. So if you think about this algorithm for the special case of an order 4 tensor, it coincides with power iteration. But now we are generalizing to a setting where there is no multilinear algebraic structure. It's just this function encoding a basis. So here is how I see that it generalizes power iteration. If f of u is evaluating a tensor at a point 4 times for a order 4 tensor, then tensor power iteration is, well, you evaluate the tensor at 3 times the point, and then you normalize and you iterate this, right? Well, if you compute the gradient of f, that's exactly the same iteration. And we have pretty good theoretical guarantees on this algorithm. Well, technically the algorithm, as I described it, gradient iteration, it's more of a practical algorithm, and it would be hard to prove that it can be used formally to enumerate all hidden basis vectors, because, for example, you may get unlucky with the starting point start at a point that is unstable but a fixed point or something like that. So when we are actually proving things, especially when we prove that this converges even under noise, we are proving it for a refinement of the algorithm that is more suitable for a theoretical analysis. But anyway, the first thing that we prove is that for the pure gradient iteration, the set of stable fixed points is exactly the vectors we are looking for, so plus minus the hidden basis vectors. And then for the actual enumeration problem, possibly under additive noise, we show that a variation of the algorithm can enumerate all the hidden basis vectors efficiently, even if the basis encoding function has been perturbed. So this answers a question that you may have been having when I was talking about spectral clustering, that I was only talking about the ideal case and what happens when you perturb. And at least we know that empirically things go fine, because I showed you those examples, say, for image segmentation. But when we did the analysis of spectral clustering, we did not do a theoretic analysis of the perturbed case. But now we have it through this algorithm. And finally, you may also be wondering, well, what's the difference between gradient iteration as an algorithm versus running gradient descent? One key aspect that was already observed in some of these special cases, in particular tensor power iteration and ICA, is that when you do something like gradient iteration, you can achieve superlinear convergence. So, for example, the method based on the fourth cumulant for ICA can be shown to have qubit convergence, even though it's only a method that uses first order information. And that's also true in this case. More generally, we find conditions which are like stronger strict convexity conditions that guarantee that this first order method will have superlinear convergence. Specifically, if G, the contrast function composed with the rth root of T, is convex, then the convergence will be of order r minus 1. So, for example, this just immediately generalizes the result for ICA, because raising to the fourth power will allow you to take r here to be 4, giving you cubic convergence. Questions?
When you said perturbation, right, that can introduce new local optima depending on the kind of perturbation.
In general, yes. So, but the theorem will put assumptions on the perturbation so that they don't happen.
What kind of assumptions?
So, let me think for a second how to say this. Well, there is a good interplay between how strictly convex your contrast is, which has to do with how deep the maxima will be, right? So the condition will say, well, you have to be somewhat away from the quadratic case, which is the limit of strict convexity, right? The function g equals t squared. When I do this composition with square root will be linear, so it's not strictly convex. But anything of higher power will be strictly convex, like t cubed.
But that's
so you have to be away from the quadratic case, first of all.
And that's the constraint on G, right?
That's a constraint on G.
But on the noise, on the perturbation,
it's like the magnitude of perturbation, but the most strictly convex you were, or strongly convex, the higher the perturbation will be allowed.
But is there a precise characterization? I mean, especially for the tensor case, tensor iteration case.
I haven't actually done the comparison, so I'm not so sure.
Yeah,
This is right. That sounds very interesting, though. Yes. Yes. So here is another example that I'm not going to describe in detail, but it also fits this model, which is sort of inspired by the work of Su and Kakade, the parameter estimation for a spherical Gaussian mixture model. I feel, though, kind of obligated to mention something else that we did recently in estimation of parameters of Gaussian mixture models that's probably interesting to anybody doing spectral methods, which is because spectral methods are frequently used for this, namely dimensionality reduction. The message is that for the problem of Gaussian mixture models, dimensionality reduction can be a very bad idea. And it's interesting because many old algorithms for estimation of parameters have as a pre-processing step some sort of dimensionality reduction, or dimensionality reduction happens somewhere in the algorithm. And what we found is that the estimation of parameters in low dimension is generically a hard problem. It was already known before by the work of Moitra and Valiant that it was hard for some instance, but actually it's not just hard for some instance, it's hard for generic instances. So if you take, for example, you can show if you take two sets of k points that are going to play the role of means of two Gaussian mixtures, then these sets of means, while being different and generic, one can choose Gaussians to put on top of them so that in parameter space these are far because the means were far, but in L1 distance or total variation distance these two mixtures are very close, which means that any estimation would be very expensive. Say if they are for dimension 1 they will be at distance e to the minus k, which means that you will need a number of samples exponentially k to distinguish them, and that would be the only hope of estimating the parameters correctly. So instead, in our work, as well as a simultaneous work of Sharikar et al., it is shown that if you don't project and you start with a problem that's in high dimension, then you can estimate the parameters of at most a polynomial number of Gaussians in dimension d efficiently. But if you project or you start with a problem low dimensional, that's hard. So this is what we call the blessing of dimensionality, this combination of an upper bound and a lower bound for this particular problem. So in summary, I presented a new algorithm for multi-way spectral clustering, which generalizes to what we could think of as an algorithmic primitive, hidden basis recovery, where data is encoded by functions generalizing tensors. And I also describe an efficient algorithm, gradient iteration, that has good theoretical guarantees for this problem. In particular, a complete enumeration of admissible contrast functions for the special case of spectral clustering. So if you want to know more, this is detailed in 3 papers. The spectral clustering aspect is in the paper, The Hidden Convexity of Spectral Clustering, which is in the archive. The blessing of dimensionality is this other paper with Anderson, Belkin, Goyal, and Voss. The more the merrier, the blessing of dimensionality for learning large Gaussian mixtures. And finally, the hidden basis recovery problem and algorithmic results are in a paper that we are going to post in the archive in a few days, learning a hidden basis through imperfect measurements and algorithmic primitive. So I'll stop here.
Thank you. Any questions for Luis? Well, that's okay.